Now, building upon what we had done in the last class, so once again, these are all the float and integer pointers, okay, and we have seen how to print them and how to do scanf. Just remember that when you're using a pointer, you do not actually need to use the ampersand because the pointer already has the address. So you do not have to use the ampersand for the variable. What normally you would have written as ampersand x or ampersand f, you can just do a scanf percent f fp because fp is the pointer to f. So there we are, fp is the pointer to f, and so we can already we have the address in fp, so you do not need to do this. Now also when you are printing, just remember that star xp actually prints the variables. That means the variable that the pointer xp is pointing towards, assuming that xp is the pointer and fp is the pointer. Star xp actually points towards the variable that the pointer is pointing towards, this here, while xp refers to the pointer itself. So star xp prints if xp is pointing towards x and x has a value of 5, then star xp prints 5. While if the address of x is say 00ff in hexadecimal, then xp would print your the hexadecimal address. Here the hexadecimal address we have printed using %x, which is the conversion character for hexadecimal notations. We can also use something called %p. Okay, so for example here we can use something called %p. %p is specifically used for printing a pointer. Okay, so if I run this, okay, and it is obviously expecting a scanf, and you can see that xp and fp are both 8 bytes long. Now 8 bytes, mind you, is not actually what is 8 bytes in DOS. 8 bytes in this machine, in my Android phone, is equivalent to 2 bytes. Actually it's the size of an integer, unsigned integer. That's what it is. Now let us say we enter 23.968754. That's for the float, and here we are. So x is 9 and its address is so on and so forth, etc. Now look at this. X is 9 and its address is OX7EE646 6D46. Okay, so this is because it is printing in the format of a pointer, that it is printing this. Okay, FEE646 6D46 FC. Okay, so this 6D46FC is here also, and the same is here also. The only addition is OX7. Okay, so that is to say that it is actually printing. That one here is a direct printing of the hexadecimal, and this is the printer form. This format is for this is the pointer format actually. Okay, so if for example if I go to this part here, and rather than printing %x, I'm just gonna make it a %p. Now once again 8 byte and 8 byte. Now I want to enter 45.56 like that. So let me just give it 10 decimal places, and when you just run it, okay, so this is the pointer format, OX7F and CFB233C8. This is the CFB233C8. This OX7F, the extension is because it's being printed in the pointer format. So you can print it either as an hexadecimal or as a pointer. In hexadecimal, it will just take the address and print it out just as a hexadecimal sort of a hexadecimal well, I mean an hexadecimal number, and in this case it is printing it out specifically in the form which distinguishes it from other hexadecimal numbers. It prints it out as a pointer. I'll give you the example where it is different. For example, there is obviously this we are printing out, say we are printing out x here is being printed out, by using star xp. Okay, so star xp actually is printing out the value of x, the same thing. X and star xp are the same thing, but we are printing it out as a decimal number. Let us see what happens when we try to print it out as a hexadecimal number. As you know, everything is expressed in binary. So if everything is expressed in binary, there is obviously a hexadecimal equivalent of that as well. So if we run it, okay, and then once again we enter, okay, so this is the hexadecimal of 9. It is basically 9. Go back and let us make this into 15. Now okay, see, x is f. Look at this line here, the second paragraph, or rather the third paragraph, if I can call these paragraphs after the second gap. See, x is f. Why x is f? Because obviously we put in 15. We're trying to put it through as we're trying to output that as a hexadecimal number. So obviously 15 is, as you know, is f. So that is what is happening here also, that when you are printing it out as a hexadecimal, okay, this is the address of it, the hexadecimal, okay, but when you are printing it out as a pointer, then this is the format that it is producing. So E6 out here, this one here, E6 D3603C becomes there. The format that is given in this particular machine is OX7F and then E6D3603C. Okay, so you can see the difference. This is the one and this is the one. This is the one where I've printed it out as pointers, and this is, so you can see that's a hexadecimal. Say 15 hexadecimal. This anything can be printed as a hexadecimal. Anything can be printed as a hexadecimal because everything is in binary, and obviously it's in multiples of bytes. So everything can be printed out in hexadecimal, even if it is not in multiples of bytes. With trading zeros and everything, we can easily print it out as hexadecimal. Except that up to 9, as you know, from 0 to 9 it will give the same result. Now you see, just go back and say make it, say, rather than 15, let's make it, say, 255. Okay, now if you run this, another small input here, 56.98. okay, press enter. So 255 is ff. You can see this is 255, this is ff. Okay, this here is 255, this here is ff. So everything can be, but let us see if what will happen if, for example, we try to print this out not as a hexadecimal but actually as a pointer. So this here we're printing out x as a hexadecimal, right? So rather than that, we try to print it out as a pointer. We are actually printing out xp as a pointer. Xp is a pointer anyway, so we are printing it out not just as a hexadecimal. We're trying to print it out as a pointer, but here we're trying to print it out as a pointer also. And this case here, as you know, this the first one is not a pointer. Actually, star xp refers to x. X is not a pointer, it is a normal variable. So we run it, okay, and let's see what happens. Okay, it'll take OXFF. So what does that actually tell you? Basically, it tells you, see, all it has done is it has taken it as a pointer, but it is not a reference to anything. Okay, we're printing it out as a pointer, so that comes out to be OXFF. So just a format change. So FF to OXFF. Previously it was giving us FF, now it is giving us OXFF. Okay, and this is the decimal value 255. It is just changed to OXFF, but it is not giving you the prefix OX 7f because it is actually not a pointer. Now this will depend upon the compiler how it will show that this is not a pointer. Here it is working, but it will not be showing you this. Maybe in Turbo C++ or other compilers, if you run it, maybe they will just give this is a pointer. This is not a pointer, you're trying to print it out as a pointer, so possible fault. Something like that will happen. Whatever it is, okay, there'll always more or less be a distinction where you are just trying to print out something as a pointer which is not a pointer and something as a pointer which is actually a pointer. See, once again, 255 printed out as OXFF. It is taking X as a pointer, the value as a pointer. That means it's an address, and the address is actually being given off as OXFF. However, in the actual storage of an address like this, it is suffixing it, or rather, beg your pardon, it is prefixing it with OX7F, and then it is giving us the address like C6E2564C is becoming OX7F C6E2564C. Similarly, C6E25648 is becoming OX7F, OX for hexadecimal, obviously it's an hexadecimal format, OX7F C6E25648. This is the difference, distinguishing it both. Although the OX is already there because it's in hexadecimal, it is distinguishing these two as being a pointer which has been printed as a pointer and a non-pointer which is forcefully being printed as a pointer. Okay. Now that was the trivial part for today. Now let us just start off with something else. Now you see, for example, now let us see how we can use these pointers. Okay, how we can use these pointers. Let me give you a classical example, some example that you will already find in Dennis Ritchie and Brand Cunningham. Let's say we have a function called swap, and you have index int y. Now, what do we remember from functions? That functions can actually only return one value. That value may be a float, a point. Value may be a float. It may be an integer. It may be a character, or it may be an address. In which case, it is a pointer. An address is obviously, we say that it's a pointer. Actually, it returns an address. It's just a value. That's all. A particular function cannot return an array. A particular function cannot return an array at all. Okay. Neither can it return two different variables. Right. So error. Two or more data types in declaration specifiers. You cannot do int. Give a comma here, it still won't work. There you go. Okay, that is obviously out of sync with the C programming language. You cannot do this. So you cannot return two variables at all. More than one value you cannot return in case of a C function. But guys, we have X and Y. So what do? There are two ways you can do this. There are two ways. Once again, you cannot return an array also. For example, if I can easily take an array inside swap by saying this. Whatever is sent here will be taken. So you won't have to mention any size. If you run it, okay, it runs, right? The reason being, I can pass it any kind of array. Any kind of array. I can have a structured array, two-dimensional array. That means two-dimensional array is basically array of arrays. So structured array, union array, whatever. All of this is done. But if I try to pass it, if I try to return from it any particular array, once again the size is unknown. Wrong. Okay, so it cannot return an array, as you can see. So in that case, it is, how is it that we can, when we are swapping, so if we make an array of 2 integers, we cannot return it, full stop. If we make an array of 2 integers, we cannot make it, we can return it, we cannot return it, full stop. So what can we do? Well, one thing we can do here, in a very naive sort of a way, we can make a structure called struct, beg your pardon, called struct two nums. Once again, two nums is a name that I'm giving it, so you can give it anything you want to. And as you know, the semicolon is very important here. I don't know how big the integer is going to be, so I'm not going to give it, and what values it's going to have. So I'm not going to make it unsigned, or I'm not going to make it a bit field. I'm going to just make it an integer. So integer x, integer y. And I am going to return here. Achha, so let me just type def it. After or before it. You can do it after, you can do it before. Let me just do it after. Type def struct two nums as to n. Run it. Okay. Yes. I mean struct. Definitely. Okay. So struct two nums. Okay. So run it. Compiles. Good. Now what I can do is I can return here one to n variable. I can return it here. So run it, it'll work. So one, see, because what is happening here, although structures more or less act in the same way as an array, however, this is a structure object. This is one structure object you're returning, so that is allowed. That is allowed. You can, although it works as an array, you can actually return one structure object or one union object. You may say that, sir, in that case there are two values that are returning. Well, in this case it works a bit differently. It works as a pointer that is being returned. In case of arrays, it is not exactly taken like that. That is how the compiler is built. If it was so that the compiler is built in such a way that if you try to return an array, then its starting address would be taken. Like, for example, an array's name obviously is the starting address. An array's name is the starting address to its elements. So if it was so that the compiler would act like this, that if it was fed an array's name, you could return it, because it would view this as a what is it? I mean, like it would view this as the array's starting address being returned, then that would be absolutely okay. That would be absolutely okay. For example, if you wanted to return here in this function, if you wanted to return here an integer pointer, you're welcome to do that. It works. If you want to return it a structure pointer, we have a structure ready at hand, 2n. Run it. Once again, it works. No problem. Right? And obviously, so like that. But it is not the case with an array. You cannot return an array, as we have seen. So one way is to do this. How do you do this? Well, it is like this. So You take and you know a very simple thing. This is how we do swapping. You take, what is swapping? Swapping is you reserve the value of one, assign the value to it, and the reserved value goes into the second one. So in temp, all right. Now temp sorry, you need another declaration. This time for a, this time it is actually for a 2n object, 2n tn, let's say. Do not name it swap because your function itself is called swap. Now 2n, now you just declared it, so it is made, but nothing is done yet on this. Now, so temp equals to x, and so temp equals to x. Then you have x equals to y. Then you have, because now x's value is destroyed, it is overwritten by y. X is now y value, that is. Now you do y equals to temp, right? So there we are. Now let's name it something better. Let's name it tn swap, so it's better. Now once we have done this, what we can do is we can do tn swap. Now you see the x and y have now been swapped, the original x and y. So tm swap dot dot x swap dot x, beg your pardon, dot x is equal to x, and we can definitely do your tn swap dot y equals to y. So the swapped x and y, x has now become the original y and y has now become the original x. Now we are putting x's value into tn swap dot x and we are putting y's value into tn swap dot y, and now we are returning this. Okay, so we just do a return, and our object's name, we can say that's a structure variable. Actually, more specifically, it's an object. Okay, return tn swap. Now run it, you'll see it compiles. Now what we can do is in main, n equals to x. Now without hampering anything else, y equals to minus 6. It is 6, that is minus 6. Y is 6 and x is minus 6. Sure. Okay, let's make it more distinct. Say minus 32. Now if you swap it, x, so now x is being printed and everything else. So if you run it, okay, here another there quickly, x is 255 and blah blah blah. Remember y is minus 32. Now we'll call the swap function with x and y. Now we call the swap function with x and y. Sorry about the clumsiness. We call the swap function. We have to actually take a variable. We have to take a variable in main. Let's call that 2n, because we have type depth it, so 2n say swap x y, swap x y, right? 2n swap x y. Now here what I'll do is I'll just do swap swap x y is equal to swap x y. So when you do swap xy, what will happen? When you do swap xy, this is supposed to work, and in the 2n, that is this, sorry, the tn swap, which is formed in that particular instance of the calling of the swap function, that one returns it as a 2n object, and this 2n object gets into swap xy. As we have seen when we are doing structures, that Akash's date of birth can be assigned to another date of birth. Similarly, this swap xy's 2n object has been assigned to swap xy here. Now when you run it, that is what is going to happen. Before this, let us print out to arrive so printf a new line again, just for the distinction. Before swapping, x is %d, y is %d, and just simply, obviously, you have to, in place of the 2%d's, you have to write x and y. X will show in the first %d and y will show in the second %d. Fine, fair enough, you got that. Now we have to write the printf for the other one. So printf \n after swapping x is %d, y is %d, and here we are going to give what is the name of that variable that we have, swap xy. Okay, so we have swap xy dot x, swap xy dot y. Run it. Now let's say we have okay. So before swapping, you can see here, before swapping x is to the last two lines. Before swapping x is 255, y is -32. After swapping x is -32, y is 255. So you can do it this way. Definitely. When you have multiple things to return, you can use a structure for that. You can use a structure for that. There's no point that you can do that. But this is not what we actually call very elegant programming. There's a reason behind this. You are creating structure variables, so you are taking up a lot of space. What are you using your structure variables for? Just for containing two values. There is no other reason for that. You are swapping two variables. You're just swapping two variables. Okay, you're swapping two variables inside a function, but you're using a structure for that. That is not a very very elegant way of programming. That is not exactly what we want. Let me show you another version. This time we're going to do it using pointers. Now, and also the returning has to be done. Returning of the structure has to be done. So all of this is taking up a lot of effort from the computer side. This time what we're going to do is we are going to use a swap function called a swap PTR. That's swap with pointers. PTR is swap with pointers. So swap PTR is refers to swap with pointers. That's what it refers to. Okay. So swap with pointers. Now what am I going to go and do inside there? I'm going to just use the look at what I'm doing. I'm just first of all I'm going to just sort out my the syntax first so that I can get it right. Inside here now what we're swapping, we are swapping two variables which are integers. Okay, we are swapping two variables which are integers. And so we will want to use this. See what we're trying to do here. Inside main there are these two x and y variables. From here, as you know from our knowledge of scoping, from swap pointers there is no way you can access it, because swap pointers is a different kind. It is totally a different variable altogether. Swap pointers is a totally different variable altogether. So obviously you will not be able to access, because it's a different scope, it's a different function. We've seen this already many times. I'm not going to repeat that. If you have an x in swap pointers, for example, that won't be visible in main. If you have an x in main, that won't be visible in swap pointers, etc., etc. But there is a point here. You see, whether it is the value of, say, for example, if I have a, say for example, this here is int x and int y. Say this int x and int y. Now you see all of these, whatever they are in the same memory. They are in different parts of the memory, as those have been designated privately to different functions. That is true. They have been designated privately to two different functions. But that is a part of the same memory. Not just a part of the same memory, they have the same continuation of the address. Okay, so for example, let us say that the address is 100, another address is 1000, another address is 5000. The address 100 will be 100 everywhere. The address 1000 will be 1000 everywhere. In the memory, 1000 only refers to a particular location, 100 only refers to a particular location, and so on and so forth. Always. Okay, so if you are pointing towards something, then whatever you are pointing towards will be the same everywhere. I'll give you an example. Let us say out here in swap pointers, you're using one pointer to point towards a memory location 1000. Memory locations are generally, as we have seen, pointers are actually in hexadecimal. But let us say that we have a memory address called 1000 and it is pointing towards 1000. 1000 is a part of main, but that's absolutely okay because it's a part of the same memory system. So from inside another function, you can point to an object or another variable inside another function. From one function to another function, pointer is allowed, and because it works, because the addresses belong to the same memory system. It was different than a different case altogether, but part of the same memory system should be different. So we will take two pointers xp and yp to point to the mains x and mains y, and here very fortunately we won't have to return anything whatsoever, just void, nothing to return. What we'll do here, simple, same story. I'll just copy and paste, in fact. Same story, but with a different flavor. Now temp will be equals to star xp, star xp will be equals to star yp, and star yp will be equals to temp. Nothing to return. Small, simple, elegant program with pointers. What is happening here? Temp will get the this is xp. Temp will get what xp is pointing towards. And what is xp pointing towards? Out here, xp is ampersand x. Similarly, we'll have a which will point towards, it's a star yp, which will point towards y. So inside xp there is x's address, inside yp there is y's address. Inside xp there is x's address, inside yp there is y's address. Okay, now fine. So out here this xp is pointing to the x of main. So when we do temp equals to star xp, it gets the value of the x of main. When we do star xp equals to star yp, the value of x's yp, the x is y, because yp is pointing towards what? Yp is pointing towards the y of main. Y of main. So y of main's value goes into the x of main, because we are doing star xp. So star xp. So basically star yp equals to star xp means take the value of what yp is pointing towards, which is actually y of main, and put it into what xp is pointing towards, and which is actually the x of main. So the work will actually happen not in swap pointers but inside of main's memory. Remember this. The instructions are executed from swap pointers, but the actual change is happening in main. Amazing, isn't it? So this is why we use pointers. Pointers are pointing towards the main function or inside the main function, and it is working. Swap pointers has the instruction, but the instruction is getting the effect inside of main directly, so we don't have to return anything. And then star yp equals to temp. This temp is obviously within star pointers, swap pointers, so it is taking the temp and putting it into what yp is pointing towards. And what is yp pointing towards? Yp is pointing towards the y of main. Okay, so now we have to call. What is the name? Swap pointers. So here's something we want. After swapping, we change that to after calling swap with x and y. After calling swap with x and y, this is the result. Similarly here we will have, now we'll call swap with pointers, and we'll pass it. We can directly pass xp, yp. We can easily do that. I'm going to just comment this line because what we're going to do is something which I want to show you. We can directly pass the addresses without calling on the pointers inside the main. So we'll do swap ptrs ampersand so we'll do I hope you understand this. Well, what is happening is, see, xp is pointing towards x, so I can send it xp, I can send it ampersand x. But what we're trying to do is, we're trying to send here the address of x. We are trying to send here the address of y. Now, if xp and yp are there and they already have the addresses, we can send it by name xp and yp. Otherwise, we'll just exclusively send the addresses to the swap pointers by ampersand x and ampersand y, and these two arguments will be caught in the parameters star xp and star yp that belongs to swap pointers. Okay, now once we do that, what will happen? Let's just copy this one line. Okay, now one small glitch remains, that here swap xy is getting, okay, so see, if I run this, what will happen? See what will happen. Okay, you see the result is the same. Why is that? Well, the reason being, we have not assigned swap xy's x and y. Once you get the swap xy back, what you need to do here is, sorry, I do beg your pardon, x y. So now we have the properly swapped values. Okay, and so x and y, the swapped value are in swap xy. Swap xy is x contains the previous y, Swap xy is y contains the previous x. So we reassign them. So mains x and y also change. So here, instead of doing swap xy dot x, we just do x and y, so that we are changing. So we're just changing. We have the change values. So now see what happens when we run it. Okay. So now oh okay, sorry, I beg your pardon, this was a problem. I was trying to print out swap expressor, sorry. So now see 32 and 255, 32 and 255. Let me be a bit, make a bit more specific. This is swap and calling swap pointers. This will be so you see now these have been swapped. Yeah, you can see specifically. Now specifically, we after calling swap with x and y, we have minus 32 and 255. After calling swap pointers with x and y, we have 255 and minus 32. The only thing is, as you can see, with using of pointers, we have saved up all of these. We have to first make a structure object, then we pass x and y, because we cannot use an array as we have seen. So we can only use a structure object. We have not done unions yet. When we do unions, you will see that unions can only hold one variable at a time. So when you hold one variable at a time, you cannot send two variables. So in such cases, what will happen? You only have the liberty of using a structure. Now when you use a structure, then what happens? Then you have to make a structure object. So you have to use that and you have to return it. And then when you return it, you have to then reassign. So I forgot to reassign this. Okay, so basically what happened was that if you just forget to reassign, you'll have the original ones back, not the swapped ones. You have to remember to reassign. All of this problem is there. Rather than that, elegantly use a couple of pointers. Simple, that's it. Elegantly use a couple of pointers. Similarly, if you have to say, for example, do some searching or whatever it is inside a particular array, you cannot return the changed array. Okay, but you can obviously use a pointer to do the work for you. You can definitely use a pointer to do the work for you. Okay, so use these pointers whenever you can. Okay, to elegantly program between functions, etc. No need to return or anything. You can work directly. This one work directly. See, after working with swap pointers, it was back to the previous one. All right, it was back to the previous one. No questions asked. The reason for that is obviously that it has worked directly. The pointers which were pointing towards mains x and y have worked directly with mains x and mains y. You did not mains x and mains y. You did not have to do any more assignments or whatever. Okay. So enjoy this video. Have a look at this properly and leave your comments.